We can use the binomial theorem for a discrete random variable x if x is the number of occurrences over a fixed number of independent trials with constant probability of success. However, while we can use it to find the probability x equals k, it's less convenient for intervals. For example, suppose a fair coin is tossed 100 times. Find the probability there are at least 60 heads. Now, the event at least 60 heads is the union of the event 60 heads, 61, 62, and so on up to 100. So our probability that x is greater than or equal to 60 is the sum, which requires computing 41 binomial probabilities. So what if we graph the probability that x equals k, where x is the number of heads in some number of tosses of a fair coin? As the number of trials increases, the PDF begins to look suspiciously familiar. This suggests we can use the normal distribution to approximate the binomial distribution. In a binomial distribution, there are n trials, and our event of interest has probability of occurrence p. Since we want the normal distribution to approximate the binomial, we'd want the mean of the normal distribution to equal the mean of the binomial, and the standard deviation of the normal distribution to equal the standard deviation of the binomial. So remember that the mean and standard deviation of the binomial distribution with n trials and probability of success p will be. So what if we used a normal distribution with the same mean and standard deviation? So suppose we toss a fair coin 100 times. Let's find the mean and standard deviation of an approximating normal distribution. So we want our mean to be n p, the number of trials times the probability of success, and so that will be, and we'll want our standard deviation to be, and substituting out our values gives us. Now, there is one problem we run into. Since the normal distribution is continuous, then for any value k, the probability x is exactly equal to k is 0. But since the binomial distribution is discrete, the probability x equals k will not, in general, be 0. And that would make for a really bad approximation. To use the normal distribution, we need to turn it into a discrete distribution. We can do this by using a continuity correction, a continuous interval whose values round to the desired outcome. Now let's simultaneously check to see if our approximation is any good. So let's use the normal distribution to the binomial to approximate the probability of obtaining exactly 50 heads on 100 coin tosses, and we'll compare that to the exact probability. So we can approximate the binomial using a normal distribution with mean and standard deviation. So we want the probability of obtaining exactly x equals 50 heads. This outcome corresponds to all values in the interval between 49.5 inclusive up to 50.5 after rounding. And so the values in this interval all round to x equals 50, and so we can find the probability we fall in that interval. So we'll find the z-scores of our boundaries, which will be and we'll use our standard normal distribution table. This is the area to the left of point 1. And we'll subtract off the area to the left of negative 0.1, which is complementary to the area that's to the left of 0.1, and that gives us Now, we'd like to find the exact value, so here we have a binomial probability with n equals 100, x equals 50, and probability 0.5, And so we find the exact probability that x equals 50. And it's the same number. And so we get a pretty good approximation. So now let's go back to our first problem. If our coin is tossed 100 times, let's find the probability of obtaining at least 60 heads. So again, we can approximate the binomial distribution using a normal distribution with mean and standard deviation. Now, the outcome 60 or more heads is really the outcomes 60, 61, 62, and so on up to 100. And we can think about these as the rounded values in the interval. And so the outcomes that we want correspond to all rounded values in the interval. And so we can find the probability we're in that interval. We'll find the z-scores. And since 10.1 is literally off the charts, the probability that we're outside beyond that region is essentially 0, so we can ignore this boundary. And so the probability we're greater is complementary to the probability we're less, and we can look up our values in the table, and we find